It's really quite useful to be able to represent sets in some sort of visual fashion. We know how to write them in set roster and set builder notation, but how do we visualize a set? First and foremost, we want to think about a universal set. So the capital letter U is reserved for the universal set, and what we can think about this as is as the universe. It's the set of all possible elements we are studying. This is not always well defined. It really depends on the context. We'll look at a couple of examples. But within this set, we may have additional sets that parse up the universe. So a very intuitive example is, let's say we create a set, and oftentimes you'll see these universal sets represented as rectangles. So in our universal set, we'll define U to be the set of all counting numbers that are, let's say, greater than or equal to 1. So 1, 2, 3, 4, 5, etc. So we could write the universe consists of the elements 1, 2, 3, and so on. Now, inside of the universe, we may have other sets, what we often call subsets of the universe. So oftentimes you'll see these represented as circles, but they don't really have to be. So here I have a set that's inside of the universe, and I'm going to define this as the set A. And I'm going to say that what lives inside of A are the elements 1, 7, and 15. So inside of the set, I could actually draw those elements, although a lot of times these sets are going to be too large for us to be able to list out these elements in the set roster notation. But for the sake of example, we have the universe, which consists of all the counting numbers. And then inside of A, we just have some subset of that universe. So 1, 7, and 15 are elements that are part of the universe. So you can see that this circle falls within the universe, but it does not contain all of the elements of the universe, and it does not contain elements that are not in the universe. So for any set that is within a universe, that set is definitely going to be a subset of that universe. After all, it lives within that universe. Now, we don't just have to have one set. We could define another set, let's say B, and that's going to consist of the elements 2, 4, and 7. So first of all, we see that one element that these two sets have in common is the element 7. And so as I draw this next set, I somehow want to capture the fact that 7 is both in A and B. Now initially, we may just draw a circle, and we may say that this is set B, and inside of here live the elements 2, 4, and 7. But I clearly see that there's an overlap between these two sets, and the way I have this drawn makes it seem like there's two separate 7s. And in sets, we know that there's no redundancy. So one better way, or more optimal way that we could draw this is to remove, not everything, but to remove these elements. And let's go ahead and scoot this 7 over just a bit, and we'll draw an overlap between these two sets, indicating that there are some elements that these two sets share in common. Now 2 and 4 are only a part of B. They do not live in the set A. Therefore, we draw them as being within B, but not in the piece that overlaps the two sets. So now this little portion here, this overlap, these are going to be elements that the two sets share in common. And we see that the only element that those two sets share in common is the element 7. And so now we have a way of not only describing the universe and describing the sets within them, but also how to show double ownership. Now, what lives inside of the area surrounding A and B? Now, we could go and define more sets if that would be useful to us, but inside of the universe, elements that are inside of this pink box, but that are not inside of A and B are elements such as, let's see, well, 1, 2, 3 is not in there, 4 is, 5 is not inside of A or B, 6, 8, and so on. There are obviously lots of elements inside of this universe that are not included in the sets A and B. Now, there are also situations where we want to describe the elements that are in the universe, but perhaps not in one of our sets. So we're going to define this thing called a set complement. And the set complement is the set of all elements that are still part of our universe that we have created, but that are not in the set that we are describing. So for example, B with a bar over it, and some alternative notations that you may encounter here would be you may see in some textbooks B with a little C at the top to denote B complement, but we'll go ahead and stick with this notation. So B with a bar over, that's read as B complement. That's going to be the set of all elements that are not inside of B and that are part of our universe. So if we look at our set B up here, and we can think intuitively as B complement as being everything else in the universe. So B complement, if I wanted to write it out for this set, well, it's the set of all elements that are not inside of B. So what is inside of B? Well, we have 7, 2, and 4, or 2, 4, and 7. So that means, since our universe consists of all counting numbers, this would be 1. So 1 is not inside of B, but it is inside of the universe. 2 is inside of B, so that is not in B complement. 3 is not inside of B. 5 is not inside of B. 6 is not inside of B, 8 is not inside of B, 9 is not inside of B, 10, 11, and so on. So the only elements that are missing here are 2, 4, and 7, because those are elements that are inside of B. So B complement, in short, denotes everything else in the universe. We could also write out what is A complement. So A complement would be the set of all counting numbers that are not inside of A. So 1 is inside of A. So we would start with 2, 3, 4, all the way up to 6. And then 7 would not be inside of there because, we're describing all the elements that are not inside of A. So then we would transition to 8, 9, until we got to 14. Then 15 is going to be missing, and start with 16, 17, and so on. We could also describe this in terms of real numbers. So if you think about A, let's define a new set, maybe not A, we'll call this C, is the set of all x such that x is just any number greater than or equal to 10. And we'll define the universe to be the set of all real numbers. Now this is not very conducive to drawing a Venn diagram, only because it's hard to list out real numbers. Real numbers are decimals, fractions, rational, irrational numbers, all of those numbers in between. So one way we would typically represent this is on a real number line. So you've probably drawn real number lines before, and on the real number line usually you have this absolute 0 here. And since C is going to consist of all the elements greater than or equal to 10, over here somewhere we would have the element 10. And since this is greater than or equal to, we would often draw a closed dot to indicate that C is going to include 10, and that it's going to include anything that is greater than or equal to that. And this continues going on to both of the infinities. So what would C complement look like? What would C complement look like? Well, that's going to be all the elements that are real numbers, but that are not greater than or equal to 10. So if they're not greater than or equal to 10, then this could be described as the set of all elements where, or such that, x is less than 10. So that would be, and with an open circle, because we are not including 10, because 10 is part of C, C complement is all of the elements that are not a part of C, therefore that would be everything over here. So in this introduction, the goal is just to get us thinking about how we can visualize sets. One way to do that is with the Venn diagram. Again, these Venn diagrams do not have to contain circles. You could do triangles. This is just the way they're commonly done.